Good day, grade 12 chemistry students. This is your third podcast. Today, we're going to look at the same learning goals we were last time. Specifically, we're looking at how to solve problems using the Q equals MC delta T question. We're going to add to this learning goal a little bit. What we're doing is we're learning how to calculate molar enthalpy, okay? So we will go through an example on how to find molar enthalpy using a calorimetry example. Okay, here's your example. So we're using a calorimetry example to find the molar enthalpy of a certain compound dissolving. And that compound that we're talking about today is urea. Okay, so we need to know, first of all, the formula for urea. So if we didn't know it off by heart, it would be given to us in the question. And I'm going to give it to you now. Okay, so this is the formula for urea. And we have 10 grams of it. That's what the question is saying. And we are dissolving that solid urea into 150 milliliters of water. And the temperature changes from 20.4 degrees Celsius to 16.7 degrees Celsius. And it's asking us to write the balanced thermochemical equation. So first of all, we have to know how to do the just balanced chemical equation in the first place before we can add a heat term to it. So here's the balanced chemical equation. So the balanced chemical equation is pretty easy because we're just looking at a blank here. You have the solid urea and it's turning into aqueous urea, meaning it's dissolving in water. And we have a certain amount of energy. I put the energy term here because I know it's endothermic. The reason why I know it's endothermic is because when you look at our temperature change, my TF is 16.7 and my TI is 20.4. So that means that I got cooler. And so therefore I know it's endothermic. So we have to figure out this term to do the balanced chemical equation. So we'll fill in this term at the end of this question. This question is also asking us to find the molar enthalpy. So I'll show you how to do that right now. To find the molar enthalpy, what we need to do is the equation for molar enthalpy is this little subscript. And we can put, in this case, we can put dissolution or dissolving, or sorry, solution or dissolving in here if we need to. And the equation is delta H divided by the number of moles, okay? So what we're going to do is we're going to have to find enthalpy first. We also know, you may not know how to find enthalpy, but we know that enthalpy is equal to the opposite of the heat formed. And we also know that heat is equal to MC delta T. Now it's key that we remember a few things. The first is that this deals with the system, our chemical equation listed above. This here deals with our surroundings. So whenever we input any information into this, we're referring to the surroundings here. So let's go ahead and let's calculate the amount of Q or heat that's formed in this, that's in the surroundings. Well, first of all, to find Q, what we're going to do is we are going to first of all realize our mass of our substance. Now, oftentimes students will say, okay, I have 150 milliliters of water, so therefore I have 150 grams, and that's great. You know that 1 milliliter equals 1 gram. Okay, I'll show you that calculation here. So all I did there was I multiplied the volume of my water times the density of water, which is 1 gram over 1 milliliter. The milliliters cancel out, and I get my unit in grams. So I know the mass of my surroundings. My surroundings is the water. I'm not going to add 10 grams of urea because urea is my system. And because urea is my system, it doesn't go into the mass of my surroundings. It's really important that you understand that. Next, what we have is the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius. And finally, we have our temperature change, which is TF minus TI, which is the following. So we have a negative 3.7 degrees Celsius temperature change when we put our TF and TI in there. Now, we know that this goes along again with our endothermic determination of this reaction because it gets colder. So now all you have to do is you just have to plug your numbers in. So let's do that. So we have Q equals MC delta T. So we have mass The specific heat capacity, we have change in temperature. Let's plug them in and let's find an answer. So I've just simply plugged in my numbers, my mass 150, my C 4.18 joules, and my temperature change negative 3.7. So our answer is 2,319.9 joules. Again, I'm not doing significant digits. If you did, you'd have to do 2, okay? And that would be 2,300 joules, or 2.3 times 10 to the 3 joules if you wanted to do that. Or we can also convert this to kilojoules, and that is just 1 kilojoule for every 1,000 joules. And we end up getting an answer of, if we round correctly, move that 3 places, negative 2.3 kilojoules. So that's the amount of energy that was lost from the surroundings and went to the system. So we know as well, if this is the surroundings, what's going on in the surroundings in our system, it's the exact opposite. Delta H equals negative Q. So the enthalpy that was formed is going to be negative 2.3 kilojoules. Any grade 10 math students know 2 negatives don't make a right, or they do. 2.3 kilojoules. Okay, this is great, but this is not our molar enthalpy. To find our molar enthalpy, what we must do is we have to find delta Hx, which is delta H divided by N. So the number of moles. We have to take our enthalpy and we have to divide it by the number of moles, again, of our system. We're referring to our system now. We converted from our surroundings to our system. Now we have to find the moles of our system, which is our moles of urea. So we're going to take our 10 grams of urea and we're going to convert it to moles. So recall our formula for urea is NH2CONH2 again. So we have to add up all those elements to 2 decimal places. And we're going to write down that molar mass now. So the molar mass I got was 60.07 grams per mole. Let's just substitute these into our equations to find moles. And we will calculate the amount of moles of urea that we have in our system. So I got 0.17 moles. Remember that we want to find the molar enthalpy, where we're going to take this moles and plug it into my equation there. Take my enthalpy, plug it in, and we should be able to calculate our molar enthalpy. So let's substitute those values in for N and enthalpy, and let's see what our molar enthalpy is. Right now, we had 0.17 moles of our urea, and that produced 2.3 kilojoules of energy, okay? Or brought in 2.3 kilojoules of energy. So let's find our molar enthalpy. So when we multiply that out, we get 13.5 kilojoules per mole. Okay, so this is our molar enthalpy. We just calculated it. So that was the first thing it asked us to find. If you recall, it also wanted us to find the enthalpy that would go into our equation. If we zoom back up here, we wanted to find this enthalpy value here. Now, if you take a look, this is kilojoules per mole. For 1 mole, that's how much energy I make when I dissolve 1 mole of my urea. If you take a look at the subscripts in our balanced chemical equation, it's 1 to 1. So therefore, we are going to take this value and put it right up here, 13.5 kilojoules. Because I'm not going to put the per mole because it is 1 mole. This represents the 1 mole here. Now, if this had a coefficient of 2 in front of it, we'd have to take this term and multiply it by 2 because this is the amount of energy released by 1 mole. So we did both things that we needed to do, and we've calculated out. This is how you find molar enthalpy. The biggest thing that you have to remember is the density and the specific heat capacity in these questions. It's the same for water. Even though they're not pure solutions of water, we assume they're exactly like water. And that was one of our assumptions from our last video. Anyways, hope you enjoyed that. That's the end of the lesson. Good luck. We'll do some more questions tomorrow.